Good day. In this video, I will discuss how to calculate the expectation value of a one-particle operator for an n-particle bosonic wave function. Okay, so to set this problem up, let's write we have n bosons. Okay, and n1 in state 1 and 2 in state 2 and so forth. Okay, and we have seen what the wave function looks like for this system in the previous video. Okay, so let me just remind you of that. So I could write, for example, so I have psi 1 through n. Okay, and this is going to have a normalization factor n1, n2 factorial, and so forth, divided by n factorial square root. And the other piece that it will have is a sum over all distinct permutations, okay, where I'm going to put the first member of that particular permutation here. Okay, and then I have Pn1. And I have n1 of these multiplied together. But I'm also going to have the rest, right? So that let me actually just say this continues here. So, I don't have much space. Well, I'll try to do it here. Okay, so I'll try to do it like this. I'm going to have phi 2, and here I'm going to have p and 1 plus 1. Okay, and this continues phi 2 all the way up to p and 1 plus n2. Let me give that 2 another try. Okay, and there are of course n2 of these next to each other, and it continues, and I have to close this here. Okay, so there are n1 wave and p1. Okay, so we have some basic permutation of n particles, 1, 2, 3, etc. And the p1, p2, p3, etc. is just a new permutation of the numbers 1, 2, 3, but such that these wave functions will be distinct. In other words, if we go back to that 3-particle example we have seen, you could have 2 particles in state 1 and 1 particle in state 2. Okay, and for example, if I have phi 1, phi 1, so 2 particles, then this is certainly one term in the sum over permutations. And if I took all permutations, then I would also, I could permute this 2 and this 1, okay, but that doesn't give me a new term. Okay, so that's not a distinct permutation, that's not included in this sum. However, if I permute 2 with 3, I do get a new term, right? Phi 1, 1, phi 1, 3, phi 2, 2. That's a new term. Okay, that's distinct from the first one. Because if I took the integral of, if I try to normalize this would just give me an extra 1, but this actually is 0. Okay, so if I overlap this permutation with this permutation here, that would give me a 0. So that those are distinct. Okay, so let's agree that this summation here denotes permutations in which the wave the one state products end up being distinct. Okay, and we know that this is a normalized wave function. Okay, so we know also that this is a normalized wave function. What does it mean that it's a normalized wave function? It actually means that if I do n1, n2, so I square everything and I integrate over all space, d1 dn, and I'm going to have here p phi 1 p1, etc. Let me just write it simple, and this is asterisk. And I have another sum because I'm squaring the wave function, phi 1 p prime 1, etc. This is actually all equal to 1. We proved that in the last segment of the previous video. Okay, so we saw there that if I do this integral, then these two sums reduce to one sum because only the same permutations, because these are distinct permutations, only the same permutations give a contribution of 1. When you do cross terms, you get 0. Okay, and the other thing is that so the two sums reduce to one sum. Okay, and each term in the sum gives you a 1 if the orbitals are normalized. And how many permutations are there? Exactly so many that this will cancel and you get a 1. So this is actually the normalization. But what we want to do here is to consider a one particle operator. So one particle operator. Okay, and what does a one particle operator look like? Okay, I will write F1 because it's one particle, and it's some operator. Okay, so generically one could write it's some operator. In first quantization, it would be some function which depends on the first coordinate, second coordinate, and the last coordinate. Okay, so that's what a one particle operator looks like. That's not the most general form actually, because I only included here coordinate dependent operators. But we don't lose any generality because you know if you had some other operator like the momentum, you could find you could do that you could do everything in the momentum basis, and you would get the same thing. Okay, so I would just keep it like this, and actually the way I'm going to write this is my the notation that I use that I introduced in the previous video. So I'm going to write this one particle operator like this, which doesn't refer actually explicitly to the coordinate basis. Okay, so some basis for particle 1, particle 2, and so forth. Okay, so this is what we want to calculate. In particular, what we're going to consider first is is the diagonal term. Okay, so what is the what we mean by diagonal term? So we will have a wave function on the left, which has n1 particles in state 1 and 2 particles in state 2. Okay, and I sandwich here my one particle operator, and here I have n1 comma sorry, I meant to write an n2 but I forgot, sorry. So I have a comma here and 2 comma and so forth. Okay, and now we know what this wave function looks like. It's the same wave function except albeit in a different notation as this psi here. Okay, so this is the bracket notation for this wave function. Okay, and we know what this wave function looks like, so we have it written out explicitly. And so our first task is to just write down this expectation value, which is something that we seek to evaluate. Okay, so we seek to evaluate this expectation value, and this is equal to, well, we have a normalization factor squared, that's n1 factorial, n2 factorial, etc., divided by n factorial. Okay, and then we're going to have integrals d1 dn, and then on the one hand, so this all falls inside the integral that I'm about to write, so it actually goes here. Okay, Let me erase that because I don't want, but that's where it's going to go. So what I'm going to have here is the sum over p permutations, phi 1, p1, etc. Let me just write it like this. I'll write my first ones, okay, p and 1. Okay, then I have my operator, my one particle operator, which is f1 plus f2 plus plus fn. Okay, sorry, this is asterisked. Okay, and I have another sum, which is p prime phi 1 p prime 1, etc. phi 1 p prime n1 n1, and the other terms too. So you would have here, you have from here to here, you have of course n1 phi 1 states, then you would have n2 phi 2 states, n3 phi 3 states, and so on. And the same goes for this part. Okay, so this is what we have to evaluate. This is what we have to evaluate. Okay, now there are several ways to do this. Okay, so one would be um, to say that this operator term is permutation symmetric, and this term times this term is also permutation symmetric. Okay, so you're multiplying two functions which are permutation symmetric. Okay, and in this case, what you could do with this operator is reduce it to a simpler term. You could just take this, instead of this sum there, you could write n times f1, for example. Okay, so n times f1. Okay, so now we have to be careful because this n factorial becomes an n minus 1 factorial. Okay, so what happens? We have n1 factorial, n2 factorial, divided by n minus 1 factorial, d1 dn, like this. And what I have here is sum p phi 1 p1, etc. And that's asterisked times an f1 only. And here on the bottom, I'm going to have p prime f1 p prime 1, etc. Okay, so I used the symmetry to reduce the expression that I have to evaluate. Okay, and now there's going to be a permutation in the sum over permutations where the number 1 is going to fall among this set. Okay, and also here there's going to be the same thing will happen. So there will be a permutation in which the number 1 or the coordinate 1 falls among the orbitals which are known as orbital 1. Okay, and the point is these are sums over distinct permutations, which means that if that 1 is permuted by other coordinates within the set of coordinates which are in state 1, that's not going to be counted as distinct. Okay, so that's not going to be counted as distinct. Okay, now, so let's consider this case for the time being, that 1 falls among P1, P, and 1. Okay, so this is the one we are talking about, and we are only going to consider permutations here, in which case 1 falls among these coordinates. Okay, so the first n1, and also p1 falls among those coordinates as well. Okay, and now I'm going to rewrite this expression slightly. Okay, so what am I going to do is I'm going to, first of all, I'm going to break this n1 factorial here into n1 times n1 minus 1 factorial. Okay, so my expression becomes n1. Now I know that 1 fell among these coordinates, so I'm going to write here an integral d1 phi 1 1 star f1 phi 1 1, which means that of these orbitals here, I removed one, and of these orbitals here, I removed one as well. Okay? But I have to write the rest of the normalization constant now, and the rest of the so I still have to write n1 minus 1 factorial, n2 factorial, etc., divided by capital N factorial. Okay, because I just took off an n1 from this factorial here. Okay, so I broke this n1 factorial into two pieces like this. Okay, and I still need the integral over the rest. Okay, so well, d2, so all the remaining coordinates need to be integrated, except that now I have, and I'm going to put a prime on this sum, the following set, phi 1, p2, etc., phi 1, p and 1, because I removed one, okay? And then I have my phi 2s and the other ones, because I'm going to have n1 multiplied here. I don't have any f's because I took out the single f1 that I had. Okay, so sorry, I have another sum which is over the primed permutations that's also primed. I have to put that prime on the sum to denote the fact that here in these sums the first coordinate was included, but I took out the first coordinate. Okay, so I took out the first coordinate, and here I'm going to have p prime 2 phi 1 p prime n1, and it keeps going. Okay, so I found n1 times this integral over the first coordinate, which is the expectation value in state 1 of your one particle operator. And then I found this term, okay, this term. And basically what this term is the normalization of a wave function. Oh, I apologize, I made a mistake. I sometimes make this mistake, apologies. This should have been an n minus 1. Okay, so let me actually erase that and fix that. That was an n minus 1. N minus 1 factorial. Okay, so sorry, that was a mistake. But in any case, what I want to emphasize now is that this is the normalization constant for n minus 1 particles, and n1 minus 1 in state 1, and n2 in state 2, and so forth. Okay, and the point is, if you want to just to convince yourself of this, take this expression and go up to the normalization that we actually evaluated, which is actually in the previous video. Okay, it is in the previous video, but I reminded you of it, right? So this is, here you have n particles, n1 in state 2, n2 in state n1 in state 1, n2 in state 2, and so forth. And that looks like this. But if you had n minus 1 particles, and you took out this particle 1. Okay, so for some reason you removed it, and you would have n1 minus 1 in state 1, n2 in state 2, etc. That would still be a normalization. Okay, so that would still be a normalization. Okay, and that's the main argument, that in this case we get. So this normalization just gives us a 1. So what we get in the end for this particular set is n1 integral d1 phi 1 star 1 f1 phi 1 1. Okay, but if I go back to the original expression that I was evaluating, what did we say here? We said that we take all configurations in which the particle 1 falls among the first state orbitals, this product of n1 phi 1s. Okay, at the same time, there's nothing unique about state 1. We could repeat the same process and do that for n2, or for state 2. Okay, and it's obvious that we have to get the same result. So if we did the same procedure for state 2, what we would get is plus n2 integral d1 phi 2 star 1 f1 phi 1 1, and we would get this. So our final expression would look like, I'm going to introduce a slightly new notation here, j and j phi j f, that's our one particle operator, phi j, or sometimes the way this is written is sum over j and j f j j. Sorry, that should be an f. Let me fix that. Okay, so and let me make it a nicer f. Okay, so that's a way to show that how a one particle operator looks when the number of states in the bra and the ket vector, if you use Dirac notation, are the same. Okay, and this makes sense because what we're saying is that, well, we should get the expectation value of the one particle operator in all the states. And how many times should we get it? Well, if there are n1 particles in state 1, we should get that n1 times. And if there are n2 particles in state 2, we should get that n2 times. So this makes some intuitive sense. Okay, so what we proved here is, let me just summarize it, is that n1, n2, blah, 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 and a one particle operator, n1, n2, blah, 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 is equal to the sum over j and j fjj. Okay, and let me just complete the notation that when I write fjj, that's equal to, this is the Dirac notation version, or alternatively you could write this as the integral d1 phi j1 star f1 phi j1. Okay, so these are all equivalent. Okay, but a one particle operator does not need to keep particles in the same configuration. It can do something else, which is kind of interesting. Okay, and we're going to study this part now. Okay, so what we're going to study now is a system in which one wave function is, let's say, nj minus 1, nk plus 1, and I'm going to sandwich again a one particle operator in between, nj and nk. That's our next task. Okay, and what does this mean? So basically by the dot dot dots, I mean that all other indices are the same except nj and nk. Okay, so on the right hand side, you start with a wave function with nj particles in state j and nk particles in state k. Okay, and here you might have n1, n2, and so forth. Here on the left side in the bra, you also have n1, n2 the same, but the only two which are different is that nj decreased by 1 and nk increased by 1. And we want to calculate this. Okay, and recall that the combinatorial factors make a slight difference here. So in other words, what we're going to have is we're going to have two different combinatorial factors, which we can combine later. So we will have n1 factorial, etc., nj minus 1 factorial, nk plus 1 factorial divided by n factorial. And this is square root. That's coming from this part of the wave function. And I need this part of the wave function, which is still, you will have n1 factorial because those are the same, but you will have an nj factorial and an nk factorial divided by n factorial. And this is also has a square root because those are normalization constants. And then we'll have an n particle integral, of course. We cannot live without those things. But here we have to be a little bit careful because we have sum over permutations. Okay, and I'm just going to write the j. Okay, you know what? The easiest way to do this actually is to put the phi j and phi k out in front. So let me actually just, because it doesn't really matter which order we put them in, put the orbitals in. So let me consider here phi j p1, okay, phi j p, but we have only, on the left side, we have nj minus 1 of these, okay, so this goes to nj minus 1. Okay, so I have, keep in mind that here I have nj minus 1 of these, and then I'm going to put the orbital k next to it. Okay, so p and j, phi k, p and j plus nk. Okay, so I have nk plus 1 of these, and then the rest. And I'm going to put here f1, my operator. Okay, so I took care of the operator, the normalization factors, but I haven't taken care of this side yet, which I write as sum over permutations, p prime, phi j, p prime 1, phi j, p and j, okay, and then phi k, p and j plus 1, phi p and j plus nk, dot dot dot. Okay, so here I have, sorry, these p's should be prime because they are the sum over prime. So these are combinations, permutations of coordinates, and here I now have nj, and here I actually have nk. Here I have nk. Okay, so I have nk, sorry, I have to put a k here, multiplying. Okay, so what happens in this case? So let's study that. Okay, And well, the wave functions are permutation symmetric, both of them. So their product has to be permutation symmetric as well. Again, I can, you know what? I will first actually do something here, which is rewrite this. So I'm going to pretty much write down the same expression again, but I want to just simplify the combinatorial factor. Okay. So first, these two square roots are bothering me, so I'm going to simplify them. But then I'm going to write down, and hopefully in a cleaner way, the rest. So basically, I can write here nj times nk plus 1 square root. Okay, and then I can write n1 nj minus 1 factorial nk factorial, etc., divided by n factorial. Okay, so I just rewrote these two square roots, because out of this I can take out an nj, out of this I can take out an nk plus 1. So those are still square rooted, but the rest are the same, so I can get rid of the square root for all the other terms. And again, I will write down that wave function. That's a little bit time consuming, but be that as it may. So I'm going to have a d1 dn sum over p. Let me write it a little bit simpler. I'll just simplify notation here. Phi j, phi j, and we remind ourselves that there are nj minus one of these, phi k, and nk plus one of these. Okay, and then there's phi 1 n1 times, and so forth. Okay, and then I have my operator, which is f1 plus etc. Sorry, I wrote that kind of wrong, but you know what I mean. Fn p prime, and here I have phi j, but I'm going to have the phi j and j times. And I'm going to have the phi k and k times. And all the rest are going to be the same. Okay, I simplified this notation slightly because I didn't write the coordinate indices, but they're according to the permutation. So if that is confusing, one must go back to this previous one. So here I have permutations in which the first nj, according to this permutation, are in state j, and then the following nj minus 1 are in state j, and the following mk plus 1 coordinates fall into the states k. Okay, and now again, one simplification I can make, and is again, I can replace this full operator. I can replace it by n times f1, because we are multiplying permutation symmetric terms. Okay, so I'm going to replace this like that. So I'm going to cross out this sum. That sum is not there, so we have this f1. And there's one other thing we have to do, since there's a factor n here, that this n factorial, I'll just put this n factorial becomes n minus 1 factorial. Okay, so let me actually do that by erasing the n factorial. So I made a change, and I made corresponding erasures. So here I will have n minus 1 factorial. Okay, and then I'm going to erase these two, but you know that what I used here to make the first simplification step is the permutation symmetry of the one-body operator that we are using. Now, the next step is to study the configuration in which out of all p permutations, the one, the coordinate, so out of these permutations, the coordinate 1 falls among these, okay, so falls into a k state, okay, and here out of the p primes, it has to fall into a j state. That's the permutation we're going to study. Okay, so what happens in that case? Well, what happens is, okay, we're going to keep this, okay, so that nothing happens to that. That's going to give us square root of nj nk plus 1. Okay, and the f1 fell in phi k. Sorry, I forgot to asterisk these functions. But so what we're going to have is an integral over d1 phi k star 1, but and then our operator f1, and we also agree that the out of the p prime permutations in this sum, we want the permutation in which the coordinate 1 falls among the state j. Okay, so we're going to have this. What else are we going to have? We're of course going to, well, these permutation factors just go along for the ride. So we're going to have n1 factorial, nj minus 1 factorial, nk factorial divided by n factorial. Then we're going to have an integral, but we already integrated over the first coordinate. So we need the rest of the integrals, which are 2 to n. Then we're going to have a modified sum over permutations. But keep in mind that we took out of the asterisk functions, the bra, we took out 1 phi k. Okay, so we're going to have here phi j p1, etc., phi j p n1 minus j, nj minus 1, sorry. Okay, and then, so there's going to be nj minus 1 of these. And then we're going to have p and j up to phi k. And how many of these are we going to have? Well, we took one out, it's here. Okay, so we can only have nk of them because we started with nk plus 1. Okay, and everything else will remain the same. So we can put the phi ones. So here you will have p and j plus nk minus 1 and the phi ones. Okay, there's no operator because there was only one, and we need another sum, but we have to keep in mind that out of this sum, so this is the p prime configurations, we started with nj phi j operators, but we removed one because it ended up here. Okay, so we're going to have here j p prime 1. Sorry for my handwriting, let me fix the j because that looks like something, a runic symbol. Okay, and this is phi j p prime nj minus 1. Okay, and phi k's, sorry, I don't, my hand is getting tired, so I will not write, but here, everything, so here you have nj minus 1, and here you have nk, and then you have the rest. And the point is that if you look at this, you have nj minus 1 up here, nj minus 1 down here, and you have the sum over the same possible permutations, because the only requirement in both of these sums is that they have to be distinct permutations in the sense that was described in the first video. And here you have nk of these and nk of these. Here I didn't specify the coordinate indices, okay? But for example, the coordinate index of this one is going to be the same as this one, but it will be a permutation p prime. And the point is that we already know that, oh, sorry, I made one mistake again. Apologies for that. That's not n factorial, but n minus 1 factorial. That was a mistake. Let me fix this. So here you have n minus 1 factorial. But you know that this entire term is equal to 1 because this is nothing else but the normalization of a system in which you have n minus 1 particles, nj minus 1 in state j, nk in state k, and n1 in state 1, and n2 in state 2, and so forth. So our final result in this case is, and let me summarize this video by stating all the results. The final result for this part is that if you have nj minus 1, nk plus 1, and a one particle operator, nj, nk, your result is going to be the square root of nj and then nk plus 1, and that needs to be in parentheses, and d1 phi k star 1 f1 phi j 1. Alternatively, you could state this as square root of nj nk plus 1. I don't know, we could say fkj. Okay, so let's summarize what we have learned, or what we have shown here. We showed that if you have the diagonal element of a one particle operator, so same wave function on each side, okay, so that's going to give you sum over L and L F L L. On the other hand, if you promote one particle from some state to another state, nj minus 1, nk plus 1, and I put here f1. So I start in a state in which I have everything else the same, but nj and nk, and nj particles in state j, sorry, nk, apologies, and nk particles in state k. And you move one particle from state j to state k, then your result is going to be the square root of nj nk plus 1 and fkj. Okay, and I have to give you one more definition here, that fkj is the integral of some coordinate. So I can write x here, I don't have to write 1. Okay, fkx star, your one particle operator fx, and fj, phi j. X. Okay, so this is one way of proving all this. And thank you very much for your attention. And we work on two particle operators probably for the next video. Also an interesting topic. Thank you very much.